Welcome to the second chapter of the course. In this chapter, we're going to talk about acid and base, and also at the end, talking about some related phenomena. Specifically, the first lecture, we're going through the basics of acids and base. And then in the second lecture, we're going to solve for acid-base systems using algebra. The third lecture, it would be using graphics. Fourth lecture, using some computer software, some programming. And then after that, we will go for some applications like titration, buffer, and also at the end, alkalinity and gas-liquid equilibrium. So that would be basically chapter 2, 8 lectures overall. Specifically in this lecture, we're going to talk about some of the basics, some of the fundamentals of acid and base. We specifically understand what is acid, what is base, a quick review of what we talked about, and what you had in general chemistry, most likely. We also talk about some quantitative description, very similar to the chemical equilibrium lecture, but tuning towards acid-base reaction. And at the end, introducing alpha notation, a very useful notation that you're going to use over and over in chapter 2, 3, and 4. So a little bit of introduction. I think it's pretty obvious that acids and base are very important in environmental system and almost in any system. So they dictate a lot of reactions and a lot of phenomena. So they can impact the system directly. So for example, at high pH, low pH, you have like different phenomena or they can also impact indirectly. For example, by controlling the dissolution and precipitation. So this is chapter 3. We're going to see that. Also, they can change the solubility of the gas. At the end of this chapter, we're going to talk about that. Also, they can catalyze many other reactions or affecting the interactions of chemical with organisms. So very important. It could impact directly or indirectly. So occasionally we had some of these impacts in chapter 1. For example, when we talked about the disinfection, HOCl, going to OCl minus plus H plus. Quantitatively, we calculated that at lower pH or higher concentration of H plus, we had more of HOCl, which was a stronger disinfectant. So that's one of the examples we had before. So pH is impacting at the end how strong this disinfectant is, considering that we have the same amount of total HOCl, OCl minus that we added initially. Or something that later we're going to see in chapter 4 is the redox reaction. For example, if we have Fe2 plus quarter of oxygen plus H plus, a very important reaction in environmental system, going to Fe3 plus water. This is obviously a pH dependent because we have this H plus as a reactant, so it will be impacted by changing the pH. So, for example, by lowering the pH, what happens? Do we have more of Fe2 plus or Fe3 plus? Exactly. So lower the pH means higher the H plus. So it's basically more of the reactant kicking the reaction this way. So more Fe2 plus is converted to Fe3 plus. So the rate of Fe2 plus oxidation. So these are the technical terms that we're going to talk about later. But here we just want to highlight that Fe2 plus converts to Fe3 plus more. The rate increases. Just two quick examples of pH that impacts, in this example, directly some of the chemical reactions that we had, or some of them that we're going to talk about. So as I mentioned, the chapter starts with some definitions, identifying some key characteristics, And then later we're going to talk about some speciation within a more complex system. But the foundation would be pretty much the same. So in short, what we're trying to answer is basically if we have same amount of acid or base added to the system, what would be the speciation at equilibrium? A very simple question, but it might be a little bit complicated when it comes to the calculation. So when it comes to acid-base, the core reaction is extremely simple. It's always about the dissociation of water. We talked about this before in chapter 1, very briefly, talking about the dissociation of water or water hydrolysis, which was the simple reaction of water liquid associated to H plus in the aqueous form and OH minus. So even the purest distilled water, you still have this reaction. So this is the reaction you can't avoid. And later, quantitatively speaking, you'll see this reaction over and over. And this would be one of the key reactions to bring it to the table to solve for the whole speciation. And we talked about the equilibrium constant of this reaction. And we mentioned that we use special designation. So this was H plus OH minus over the activity of the pure liquid, which is basically 1. So this can be simplified to H plus OH minus. And we call this K, KW. And this KW would be 10 to the minus 14 at 25 degrees. So basically the simple reaction is the most important reaction in the context of acid-base. So later we want to see when we introduce something, how it changes this reaction. And depending on that, we can talk about whether that's acid, base, strong base. So, but the core would be always this reaction. So to quickly talk about the Kw as a function of temperature, the sort of a Van Hoff equation we had. So if water dissociation is an endothermic reaction, how does Kw changes at higher temperature? So does it increase or decrease? So very simple question. So if you remember, we had ln K 1 over T, and we had two different profiles. One was endothermic, one was exothermic, and then the slope was minus delta HR at the standard state. Which one was endothermic? So the minus slope was endothermic, exactly so. And this was exothermic. So as mentioned, water dissociation is an endothermic process. So how does it look if we have Kw over T then? Instead of ln, we're basically looking at the actual value of K. And instead of 1 over T, working with T, because that's what we're looking for. What's the dissociation constant as we increase the temperature? How does this look like? Why not linear? So you're basically saying something like increasing. Yeah, I see the point, yeah. Exactly. So some non-linear behavior, but for now, let's say just increasing. So again, this would be an endothermic process, and this would be a non-linear. So this would be something we're expecting for water. And specifically when we look at the literature, we see that the actual graph is also very close to what we were expecting. First, it's increasing. Second, it's non-linear. So now we see that at 25, it's roughly 10 to the minus 14. Higher temperature, for example, 60, is roughly at 10 to the minus 13. So this means the pH of neutral water, if it's 7 at 25, is a different value at higher temperature. So it decreases at higher temperatures. So a few more basic concepts on acids and base. It's distinguishing between hydronium and proton ions. So when we talk about water dissociation, we mentioned that in the form of proton and hydroxide, but proton ion is extremely active. So proton can also react with water. So proton can react with water to form hydronium, H3O+. So this is actually what we have in reality. So in reality, we don't have H+, but rather we have H3O+, hydronium. Or if we just combine these two reactions, in reality, water hydrolysis would be something like this. Sorry, this would be in reality. And this would be hydrolysis in reality. H3O+ is also reactive, so they can also react with water. So this reaction can progress, so it can further react. So we get H3O++ plus water to form H5O2+, and so on. So this can also react with water and then forming more and more other species. So it would be like if this is H3O+, it can also react with molecules of water in the surrounding. Yep. H5O2+. So basically it seems we don't have H+, but we have a bunch of H3O+, then H5O2+, or in the form of, in general, H2X plus 1, OX+. So that would be basically a combination, which the dominant one is basically the first one. So we normally don't care about different species in terms of whether this is this one or this one or this one. Rather, collectively, we call them hydronium ions. And the good news is that for the sake of simplicity, we stick to this reaction. So we're going to use this reaction, but in reality, this is not the reaction that is happening in water. Rather, it's something like this one with an extension of going more and more in terms of the reactivity of the hydronium ion. So sometimes when you see this species, it's basically because there is a way to describe the proton ion. So now we have information about water electrolysis as the key component, as the key reaction. In acid-base, we can define acid-base like in a very simple term. We know H plus and OH minus are related to Kw, always. The product is Kw. So any increase in H plus it means decrease in OH minus and vice versa. So based on that, we can define the solution to be acidic when we have more H plus than OH minus, or basic when we have OH minus more than H plus. A very simple description. So we can call that alkaline or basic solution. So for pure water, the species we have is basically H2O, H plus, and OH minus. At equilibrium, we have Kw, H plus, OH minus. And based on chapter 1, one of the assumptions of charge balance, all the positively charged species, which is only H plus, is equal to all the negatively charged species, considering their concentrate activity and also the charge value, which in this case is +1 and -1. Then we can combine all of this to say Kw is H plus the power of 2, or at 25 degrees C, H plus is basically 10 to the -7, or pH, which is a minus log of the activity, would be 7. So for neutral pH or neutral water, we have pH of 7. At 25, pH, if it's greater than 7, which means the concentration of H plus is less than OH minus, this would be basic. And then pH of less than 7, this would be acidic. And obviously this would be different if we're dealing with a different temperature. For example, at 50, this would be 6 point something. So 6 point something would be the threshold of neutral. And then beyond that would be alkaline, and lower than that would be acidic. So anything that could interrupt this equilibrium, which means we're talking about acid or base. So it would be very simple to look at acid-base from that perspective. It's all about the dissociation of water and how that reaction is impacted. So now let's look at different types of acid and base. For this lecture, we're going to talk about the two common ones. So in addition of H plus coming from H2O in the system, we can also introduce something that already has H plus, or already introducing H plus to the system. And in that case, we're basically increasing the concentration of H plus, or the activity, to be more accurate. So imagine you have HCl, it dissociates into H plus plus Cl minus. And we know the K value, let's say, is way bigger than 1. So it's fair to say if you add 1 mole of HCl, you're producing 1 mole of H plus. You're introducing that to the system. Or to be slightly more accurate, what happens is basically when you add H plus to water, then you're producing hydronium plus Cl minus. So in this case, what you did was you introduced something that is directly introducing H plus. Or it could be something not as strong as this one, like in terms of the K value. So this K value is just leaning very much towards the product. Or it could be something like acetic acid, CH4COOH, can also introduce proton. This time K value is a very small number. So the difference between the two, if you add 1 molar of this, you get 1 molar of, roughly 1 molar of proton. But here, if you get 1 molar of acetic acid, you might get a tiny amount of H plus to the system. But still, you're introducing H plus by introducing this species. So in this case, we call these two Bronsted acid. So those are the and this would be the conjugate base or Bronsted base. So this type of acid and base are those that are directly introducing H plus to the system. So this is sort of a direct introduction of proton, and this is pretty obvious, pretty simple in terms of describing it. You're adding something that is impacting the acidity. But sometimes we add something that doesn't have a proton ion, but rather it's promoting water hydrolysis. So imagine you're adding copper 2 plus. Copper 2 plus doesn't have any proton. So when you add it to water, basically what happens is you're forming copper hydroxide. You see that in chapter 3, plus H plus. So by adding copper that doesn't have any proton, eventually you're producing proton. So this would impact the pH. So we call this kind of acid, it's a Lewis acid. And the conjugated one would be Lewis base. So the difference between the two, this one has H plus. This one doesn't. But eventually they both produce H plus. So they're both acid, but different kinds of acid. So now we have, back to chapter 1, we added KCl, the first question of the exam. It impacts the pH in a different way. It impacts the ionic strength and also impacts the activity coefficient and eventually impacts the activity of proton. But here it's also impacting the pH, but in a different mechanism because it's a Lewis acid. So it impacts the pH. Okay. So to summarize what we talked about, water hydrolysis is the core always. So this would be water dissociation, water hydrolysis. That's basically different terms we use. Or dissociation, let's call it. We have also Bronsted acid, which you have the proton ion directly, or you have Lewis acid. Which don't have any proton, but eventually you're introducing, in this case, showing hydronium to the system. So generally speaking, whatever that eventually introduce H plus to the system is an acid. The opposite would be for the base. So for this chapter, we all talk about acid, but opposite of what we're talking about, it would be base. So it would be conceptually the same. So now we know what is acid. We want to talk about acid strength and similarly base strength. Another feature of when we talk about acid. So assume you have 1 mole of HCl. The question would be eventually how much you have dissociation to H+. So that's basically more dissociation means a stronger acid, but less, it would be a weaker acid. So here, I'm not sure if you can see it, but this is basically a sample molecule. So this is HA, a common terminology that we're going to use over and over. HA is basically, A is that conjugate base, H is the proton. So let's assume this is HA. You see this is a proton, and then this is the negative ion. So this would be HA then. In the case of strong acid, it fully dissociates into H plus and A minus. All the molecules dissociate. But in the case of weak acid, you still that HA still exists, and some H plus, A minus. So that's basically conceptually the difference between a strong acid and a weak acid. So we have two different approaches to this. 1 mole of HCl doesn't increase or introduces more H plus compared to acidic acid, or we need less HCl to increase the 1 unit of pH compared to acidic acid that we need a lot. So one of the key reactions when it comes to the acid itself, specifically for the weak acid, is that this would be the standard method we write the reaction. So we write it in the acidic way, so that means it's dissociating to proton and the negative ion, not the opposite. And for this specific reaction, we can designate a special K. So the general K would be A minus, as always, H plus over HA. And if it's written this way, then we can call this dissociation constant or acid constant. So a little bit on the terminology. This is the protonated version. So it is protonated. This is deprotonated version, or species. And then the reaction is in this direction. So that means the deprotonation is happening. So larger Ka, does it mean stronger acid or weaker acid? Stronger. So larger, that means it's pushing this way more. So it's producing more of H plus. So basically stronger acid. And we can define a threshold to define like whether this is strong or weak acid by looking at Ka of greater than 10 to the minus 2. So this is basically a strong acid. For example, for HCl, Ka is 10 to the power of 3. So a very strong acid. And Ka less than 10 to the minus 2, this would be a weak acid. For example, for the acidic acid we talked about, Ka would be 1.74, 10 to the minus 5. So you see a significant difference. So acidic acid doesn't want to deprotonate, but HCl is in favor of like the reaction to proceed to fold deprotonation. So as you've seen probably before, we normally use pKa, which is basically similar to pH in terms of the definition, mathematical expression. So pKa would be minus log 10 of Ka. So all the standard tables, when you see it, is normally written in pKa. So we can redefine of the threshold of strong and weak acid. So pKa of less than 2, this would be strong acid. And pKa of greater than 2, this would be a weak acid. A quick way to look at the standard tables to see something if it's weak or strong. So that's also about acid strength. The other thing is whether something is monoprotic or versus polyprotic acid. Another definition that we're going to see. So that all depends on how many protons they can release. So very simple. Monoprotic, it's something like this one that we talked about. There is only one proton per molecule of acid. So A minus plus H plus. And then we get basically the Ka or pKa for this reaction. But sometimes we have more than one proton per molecule of acid. So in that case, it's a polyprotic. It could be diprotic, or it could be triprotic acid. So the diprotic could be something like H2A. And now we have step-by-step dissociation or step-by-step deprotonation. Again, it's written in the standard notation. So it has to be deprotonation, only one step. So it would be first HA minus plus H plus. We call this one Ka1 or pKa1. And then HA minus is deprotonated to A2 minus plus 1 proton. Ka2 or pKa2. Obviously, you can combine the two, H2A all the way to A2 minus plus 2H plus, and then you know K value would be Ka1 times Ka2, what we've learned in chapter 1. But this is the number you get from the standard table when you look at for example, diprotic acid. And that number is specifically for each reaction written in this way and for only releasing 1 mole of proton. So as a quick example, we can look at carbonic acid. What kind of acid is this in terms of monoprotic, polyprotic? Polyprotic, okay, exactly. Why is that? So we got 2 proton per 1 molecule of the acid. So what is the dissociation, the reaction? HCO3 minus. Exactly. So one mole written in the way that H plus is the product. The next one. Exactly. So this is a very important acid. We're going to cover that more and more in lecture 9, the gas-liquid equilibrium, and then later for chapter 3 also. So obviously the Ka1 would be the activity of the product, H3, and then H plus over the reactant. Then for this one also the same. So carbonic acid, bicarbonate, or uncarbonate. So a very important diproduct acid, which is also a weak acid. So when we look at the tables, we see that there are pKa1 and pKa2. This one is roughly 6.3, I guess. This one is also 10.3, both greater than 2. So these are weak acids. So we all talked about acid, but then base, as I mentioned, it would be exactly opposite. The equilibrium constant of a base is directly related to the equilibrium constant of the conjugate acid. So here in this example, we just want to see that relationship. So here, the acid dissociation constant of HA is Ka. We have that information. Now we want to use that to look at the equilibrium constant of this reaction. So basically what we have is reaction 1, let's call it, which would be Ka. It has to be for the standard format in which we're producing proton. So this would be Ka. And then we have this overall reaction. Let's call this reaction 3 of A minus plus H2O, HA plus OH minus. And what is K3 then? So we have one key reaction that we have the information. What is that reaction? Exactly. Water electrolysis, as I mentioned, is the key part of your speciation. A very important, it's sort of a bridge because you have H plus there, OH minus. Also, you have the value, Kw is a known value. So this could be a great bridge between to do the speciation. So H2O going to H plus plus OH minus. You have, it's a known value, Kw. So K3 is somehow related to Ka and Kw. So how do we make reaction 3? Reaction, reverse of reaction 1. Exactly. And I'm sure you know how to deal with the reverse of a reaction in terms of the K value. So then K3 would be the product of the reverse of reaction 1, which would be 1 over Ka times the K of the reaction 2, which is Kw, or this would be Kw over Ka, which we call the dissociation constant of the base, Kb. And that's basically how A and B, or dissociation constant of acid and base, are related. The product of the two is always Kw. And this is basically the conjugate base of that HA. And this reaction is the format of the reaction, the standard reaction we write, in which we are forming OH minus instead of H plus. But you don't see this often in this course. So it's very similar to what we talk about in terms of the acid, but we focus on the acid just to avoid confusion. So as I mentioned, A minus is the conjugate base. For HA, therefore Kb minus Kw over Ka, or Ka, Kb is Kw. Or we could do a log, minus log of both sides, and then it would be pKa plus pKb is equal to pKw, which at 25, this would be 14. a very simple but useful expression. So if, let's say this one, Ka value is 5, then, sorry, pKa of this one is 5, then pKa here is, pKb is 9. So always the combination would be 14 if we're dealing with temperature of 25 degrees C. So the standard tables, that's the reason why it's always either acid or base. So if you have the acid value, going for base would be very straightforward, because the combination would be always pKw at that temperature. Because the standard tables are reported at 25, so the value is always, the combination would be always 14. Okay, any question? So the last part is alpha notation. I remember the first time I had a similar course, and the instructor was talking about alpha notation. I mentioned, oh, this is sort of useless. It's basically rearranging a little bit of like here and there, and then getting something and defining a new term, alpha. But trust me, this would be extremely useful. Like you'll see why. Because it's basically a great bridge between what we can manipulate, which is pH, and then the speciation. So we're going to talk about that a bit later. So let's assume you have HA going to A minus plus H plus. So this is a weak acid. Let's assume it's a weak acid, because all of this alpha notation, the whole point is for weak acid. Strong acid, the math is pretty straightforward. You add 1 mole of HCl, then the pH is, all of that would be in the form of H plus, H plus. And then that fraction is way bigger than 10 to the minus 7 of pure water, then it all dictates the pH. So the pH would be minus log of 1, which is 0. So strong acid is very straightforward, strong base the same. But here is all about the weak acid. The calculation of weak acid is more complicated. So let's assume you have HA, you're in the lab, you add a certain amount of HA to the system. This is something that you have control on. So let's call that one the total acid that you're adding. Eventually, the total acid you're adding, let's say acetic acid, it would be either protonated acid, acetic acid, or some of them would be deprotonated from the mass balance point of view, right? If it's a very weak acid, no dissociation, so pretty much all of that in the form of HA, or if it's a stronger acid, this would be mostly this one. So this is a known value. This is something that you're adding. This is something that you need to calculate, right? When you add, you don't have any control. It reaches equilibrium. So we want to see what's the distribution at equilibrium. So then we can define alpha 0 to be the ratio of the most protonated acid, or the most protonated species, to the total. Also, alpha 1 is the first deprotonated one to the total. And obviously, alpha 0 plus alpha 1, what is it? Exactly, it was 1. Let's do the math, this 2, and also consider this one. So here you might ask, what's the point? You wanted to calculate HA, you wanted to calculate also A minus, and this is a known value. But now you're introducing these two, which this one is also an unknown. So we don't know what is alpha 0, and we don't know what is alpha 1. So 2 unknown for each. But now, if we can relate alpha value to something that we know, which is Ka of the reaction, a constant, and then the condition, which is pH, then we can quickly go back and calculate the individual species. So now we want to relate these two to something that is easy to measure, which is pH, or a constant, which is pKa. If we have that, this would be a great bridge. And this would be very useful later when you have a more complex matrix of species. And specifically when we look at that Excel spreadsheet, you see that alpha is the first term you're always calculating. Because once you have alpha, this is known, you can look at the species, what we need eventually. So now let's see how alpha, we can define alpha, relate that to something that is more easy to work with. So let's first assume ideal solution. So that means we don't need to deal with activity, rather staying with the concentration. So then Ka would be A minus H plus divided by HA. So no surprise there. And now we had also alpha 0 to be HA, how we define alpha 0, over total A. So we can a little bit expand the total, then it would be HA divided by HA plus A minus. So basically, that's what the total is. And now, based on this one, let's just rearrange this one a little bit. By rearranging this one, we could say Ka times HA times prot. So I had this expression, a Ka expression, product over reactant. Here what I did was just rearranging it. I have A minus as a function of HA, H plus, and Ka. And now I had this definition for alpha 0, expanded total A, and now I want to bring this here. So if I do that, then alpha 0 would be HA divided by HA plus Ka, HA divided by H plus. Now you see that we can basically simplify it by getting rid of HA. So what we get is 1 over 1 plus Ka over H plus. Or if you do a little bit of rearrangement, so then alpha 0 would be H plus plus Ka. So now we achieve that goal of connecting alpha 0 to something that is measurable, which is the pH, or something that we can change, and then something that is constant. So I give you the pH, you have the Ka for the reaction, you eventually tell me, for example, what's the ratio, what's the value of HA, what's the value of A minus. Very straightforward and very useful. So for A1, this would be 1 minus alpha 0. So what you get for A1 is Ka H plus plus Ka. So a very practical way to calculate the speciation for a weak acid. We're using alpha 0 and alpha 1. And this is how we basically prove the expression for a monoprotic acid. We can basically do the same thing for diprotic and triprotic acid as well. So in that case, we have alpha 0, alpha 1, and alpha 2. Also for triprotic, it would be all the way to alpha 3. So, and then the proving that would be pretty much the same as this one. You're not required to do that. Although one of my instructors asked us to do it for the triprotic, which was a pain. It's basically the same procedure, but it would be more involved. But you're giving this one. So basically this is what we talked about, which we just proved. Always the combination is equal to 1. Diprotic, you have all the way to alpha 2. And then this is basically what you're getting for each different alpha. And you know alpha 0 is always the most protonated, which in this case is H2A, over the total. So this would be HA minus over the total, and this would be A2 minus over the total. And this one would be obviously H3A over the total, H2A minus, HA2 minus, and A3 minus. So you can quickly, by looking at these constant and also the pH, basically calculate how much of each individual species you have. And obviously this one would be the simplest one. It's HA over the total, or A minus over the total. So now I think we all agree that this is a very good notation. It's very useful because it's working like a bridge. And then you see that when you look at the spreadsheet, when you change the pH, you can quickly calculate alpha, and then the following would be calculating the speciation, which would be pretty simple. So a quick example. This is basically this infection, the same example we had before. Now we want to plot alpha versus the pH. So we want to look at the pH of 0 to 14 and see how the ratio of the protonated versus deprotonated is impacted. And we know basically this is a stronger disinfectant. So we're looking at the profile of the strength of this infection as a function of pH using alpha, because alpha is eventually and directly related to the concentration of each individual species. Alpha 0 is related to this one, alpha 1 is related to this one. So, and then we have this graph, and then we want to see how the plot is. So we know alpha 0 in this example would be HOCl over the total, and then alpha 1 is this would be, OCl minus over the total. Also, we know that alpha 0 is H plus over H plus Ka, and alpha 1 is Ka H plus Ka. So here what we're going to do is basically changing H plus, which is our x-axis. And for each H plus, we eventually calculate alpha 0 and alpha 1 as y-axis. And we have all the expression to do that. You give this a value, then the same here. You have this one, you calculate this one, and also later this one. Straightforward. So mathematically looking at specifically these two expressions, what happens when H plus increases? So let's assume a very extreme case of pH 0. A lot of H plus. The concentration of H plus is very big. What happens to alpha 0 and alpha 1? Or like how these two are impacted. We know these two work in opposite because the combination is always 1. If alpha 0 is increasing, alpha 1 has to decrease. So the simpler one is looking at this one, right? How does it change if we increase H plus? So alpha 1 is decreasing, so alpha 0 is increasing. So that means alpha 0 is increasing, alpha 1 is decreasing. Or in the pH scale, higher the values of H plus activities means lower the pH. So at lower pH, alpha 0 is 1, alpha 1 is going down. So can we say at some point alpha 0 is very big, that is just the dominant one, and alpha 1 is almost equal to 0? Because the combination is always that. So let's assume we have a very high concentration of proton, and that concentration is significantly big and bigger than this guy. So eventually this term is equal to 0. So what part of this graph is it? Is it this part or is this part? So the left. So the left, roughly, initially we're at this point in terms of alpha 0, alpha 1, sorry. This alpha 1, we know that is OCl minus divided by the total. And because the combination is always 1, at that point, at that range, so this is very qualitative. The values are not the most accurate. So, and vice versa, at a high concentration, alpha 0 is equal to 0, and alpha 1 is equal to 1. So it seems alpha 0 is going down, alpha 1 is going up, right? As a function of pH. So it seems they're crossing one point because they have different behaviors. So at some point, alpha 0 is equal to alpha 1, which is equal to 0.5, right? The combination is always 1. If they're equal, this would be 0.5. Or what it means is that alpha 0, which is H plus plus Ka, is equal to Ka H plus Ka. What does it mean here? Exactly. At that point, H plus is equal to Ka. We're working on the pH scale, so this would be pH is equal to pKa. So what does it mean? So assume this is 0.5. That happens at alpha of 0.5, right? Alpha of 0.5. We mentioned that pH value would be equal to pKa, and pKa is 7.5. So basically what we have is so this is the intersection of the two. So if we then it would be and then so this is a very important information. By looking at alpha graph as a function of pH, you can look at the intersection, and this pH would be pKa of the acid. So one question of the exam, which trust me, you probably by now know that these are probably in the exam, is that sometimes you have the opposite situation. You have the graph, and you really don't know what kind of acid is that, but you're given this graph because generating this graph can be done experimentally, right? And then you just need to figuring out this intersection, if this is for monoprotic or more intersection, and these would be basically the pKa value. And then you go back to the table, you find the pKa value, and then you can tell what kind of acid and what acid is that specifically. So by knowing this information, that this intersection, the pH value is corresponding to pKa. And if it's more than 1 pKa, it would be pKa 1 and then pKa 2. Make sense? So that's one very important information from this graph. The other information is that alpha 1 is an indicator of the concentration of HOCl, the most protonated version. So because this is basically a constant. Alpha 1 is also a OCl minus. So then you can quickly tell at a given pH, let's say 8, then what is the concentration of the green of HOCl and what's the concentration of the orange, which is OCl minus. Very quickly you can tell the ratio of the two. So now the other thing is, so that's the second thing. The other information is that what is this region? We get this region. What is happening in this region that it doesn't happen in other regions? It's always at equilibrium. Exactly. So it's changing. We don't care about whether it's quick or not until the titration lecture. But now, in this region, things are changing as a function of pH. So let's say if you're here in this region, you change pH from 1 to 2. The contribution of HOCl, OCl minus, it doesn't change, right? Because it's not in the pH sensitive zone. So this is basically the pH active. So then we can ask the same the question we had in also chapter 1. We mentioned that lower pH is more useful for having a stronger disinfectant, because lower pH, it means we have higher HOCl. But is it always true? It's not. It's true as long as we're in this range, because here it really doesn't matter. pH 4, pH 2, pH 1, we have almost all HOCl. So it's not pH sensitive. So that could be a revision of the question we had before. And this is a very practical graph also. As I mentioned, 3 layers of information: pKa, then the active zone, and also the exact value. The graphical solution lecture, which is not the next one, but the one after, is all talking about how we use graphs to talk about the speciation. Okay, so to quickly overview what we talked about, we introduced a generic acid reaction, acid-base reaction. We're interested to look at the acid reaction, but base would be pretty much the same. We introduced this standard notation, A minus plus H plus, always producing 1 mole of proton, which was the case. And then we introduced this Ka, as always, the product over the reactant. And then we also introduced pKa, which is basically an easier way to describe. And we mentioned that we might have more than one release of protons, so might get different, or Ka1, Ka2, and so on. At the end, we introduced the alpha terminology, which would be alpha 0, the most protonated over the total. Alpha 1 was the deprotonated, the first deprotonation over the total. And then also we linked alpha 0 and alpha 1 to something that can be changed, which is pH, and something that is constant, which is Ka. And eventually we looked at how alpha is changing as a function of pH, which was something like this. This was basically the pKa. So in the next lecture, we're going to basically describe a more involved system, bringing more and more species to the table, and then calculating the pH, or vice versa. At a given pH, what would be the distribution of the species? And the tool that we're using is, the next lecture would be algebra, the following lecture graphs, and then the lecture after that, it would be some computer software.